Now let's put all the costs together in one table and see how the two representations trade off. This table gathers the costs with the reason for each. Remember, n is the number of vertices, m is the number of edges, and the degree of u is how many edges touch u. Space. The matrix needs big O of n squared, a fixed grid. The list needs big O of n plus m, one head per vertex and one node per edge endpoint. Has edge. The matrix is big O of 1, a single index. The list is big O of the degree of u, since its scans use chain. Neighbors. The matrix is big O of n, the whole row. The list is big O of the degree of u, exactly the real edges. Add edge. Both are big O of 1, just a fixed number of writes or inserts. Notice the matrix and list trade places. Whatever the matrix does fast, the list does slow, and the other way around. Now the big picture. Which representation uses less memory? It depends mainly on density, how full the graph is. At very small sizes, pointer overhead can also tip the balance. This chart plots bytes against the number of vertices for 3 cases. The purple line is the matrix. It climbs steadily because it is always big O of n squared. The green line is a sparse list, where the number of edges is about the same as the number of vertices. It grows linearly and stays comparatively low. The red line is a dense list, where almost every pair of vertices is connected. It climbs right past the matrix. So density decides the asymptotic winner. The matrix cost never changes. The list is cheap when sparse, but expensive when dense, because then m itself grows to big O of n squared. Real numbers make it clear. Take a social graph of 1 billion people, each with a few hundred friends. A matrix would need 10 to the 18 cells. The list would need a few hundred billion entries. That is a gap of about 1 millionfold. This is why the choice matters, and why it is not a matter of taste. Predict first. A sparse graph with V equal to 1,000 vertices and E equal to 2,000 edges. How many cells does the matrix hold, and how many total entries does the list hold? Pause and work it out. Here is the answer. The matrix holds V squared, which is 1 million cells. The list holds V plus 2E, which is 1,000 plus 4,000, so 5,000 entries. That is 200 times fewer slots to store. One more check. A road network with 6,000 intersections and about 24,000 roads, so M is about 4n, which representation uses less memory, and why? Pause and decide. The list wins. M stays close to n, so big O of n plus m stays far below the matrix's fixed n squared grid, which here would be almost all zeros.